All right, good afternoon and happy Saturday. We plan on doing the LeetCode Daily Challenge for today. So it's September 2nd. And let's see, share my screen here. Hide that. Okay. Extra characters in a string. Minimum number of extra characters left if you break up string optimally. Oh, already have a solution here. Okay, well, here. I guess I already solved this. Okay, so let's see. Yeah, looks like I solved this 4 months ago, so it's fairly recent. Okay. Okay, so you can break it up to two substrings, leet and code, skip the S. Okay, 50. Okay, so this one will just do DFS, right? Either skip or include. Okay, so the game plan. Here, let me keep track of what time it is. 2:57 in the PM. Okay, so the game plan is to place strings from dictionary into a set for O1 lookups. And then we can consider the substrings that match. And this is only 50, so it doesn't have to be very efficient, right? So n equals 50. So quadratic is fine. Time would be accepted, even a cubic would be as well. Okay, so yeah, this one we'll call, I'm gonna call this thing our dictionary D. Oh, no, it's a list. So I'll just call it an array. This guy will just call S as a string. So scene is the set of the array of values in the dictionary. And then we can do def go 0. N is cardinality of the input string s. So if I is equal to n, then that's when we return 0. That's in the recursive stack would bottom out and start to unwind optimally. I have no my music. What's this? Okay. Okay, so return go return this thing. And we either have two options, right? A is with or without. How about with or without? With only occurs if there's a match, or with or without. I guess it could be include or exclude. Include, exclude, just since it says matchup. Return the minimum of include and exclude. Include would only be if the remaining characters are in the set. So we'll just go through this one by one. Set to some arbitrary infinity value, infinity, and 9 plus 7. Doesn't matter. We'll fix that up later. But exclude is the cost is 1 plus go, I plus 1. So then for each candidate in the set of scene values, I guess if we're just going to iterate through it, we don't need to do this, right? For each candidate in the pivot string, just call this thing a scene, fine. This guy can be a, it doesn't matter, I guess, right? N is the length of a, the array of characters, candidate and scene. So N is the length, and we'll just say K is the length of the candidate. I plus 1, or I plus K is the strength of N. Then we can say, and a sub to I plus K equals the candidate, right? That substring is equal to the candidate. Then we can say include equals the minimum of itself and go I plus K using that candidate value. Okay, something like that should be 1. Okay, that looks good. This one should be 3. That looks good. Okay, and then we'll minimize it, right? Otherwise, it'll run into Tilly. Okay, submit 257, 301. Okay, cool. 301, it's accepted. Oops, 01, about 3 or 4 minutes, 4 minutes for the implementation. Implementation in Python 3. Oops, Python 3, which is accepted. Yay. Okay, and then so that's top down, and then we can do bottom up. All right, it's 302. So this is the R2 dynamic programming, right? Should be able to do this bottom up. Right, so our explicit DP memo, infinite value multiplied by n plus 1. DP sub n equals 0 is our base case. So here, make this look cool. Here's our memo. So this memo would correspond to the cache, basically the optimal value for each of these ith states as a recursive stack unwinds. This is the base case, right? So this would correspond to this guy. So I guess I can grab this, stick it here. Grab this, stick it there. Okay, just have a corresponding mapping. Return DP sub 0, so that corresponds to the initial invocation of go here for 0. And then for I in range in reversed, right? So we're basically explicitly mimicking the recursive stack unwinding. So we can grab, oops, yeah, oops, let's just grab this. This is our DP state that's now explicit rather than implicit. And then this is also our DP state, which is implicit rather than explicit. And then our DP state will be the ith state here. So let me grab this, stick this down the bottom. Okay, this goes up here. Right, so this is the corresponding bottom-up solution. Ith states optimally built upon themselves. Okay, 302, 304. That looks good. Okay, cool. Nice. That's awesome. Okay, about 2 minutes for bottom up. So bottom up can be tricky in that we have to explicitly state all the possible memos, base cases. Here's not too bad, right? But for other DP solutions, it can be more difficult to come up with a bottom-up solution. So we could potentially do memory optimization. We had some kth maximum, but it's up to 50, right, for the dictionary. Yeah, this is about as good as we can do. Okay, cool. So yeah, this is the R dynamic programming. So you'll see me basically go through all possibilities, add the memo so we don't solve each subproblem more than once. And we basically turn it upside down by explicitly stating the base cases, explicitly having the memo as well, rather than storing it on the recursive stack. And then we explicitly mimic or simulate the recursive stack unwinding by going from n-1 to 0 inclusive, returning the 0th value, which is the original problem itself, at the topmost invocation of Go. So we recursively go from here to there for each ith state, right? From we go bottom up, it's from 0 to n. And then as the recursive stack unwinds, we build optimal solutions upon themselves, right? And that's explicitly stated here. So yeah, if y'all have any questions, let me know. I mean, I'm not an expert or anything, but I have been studying this for a handful of years now. Yeah, okay, cool. Pretty much the same thing in a handful of languages. All right, I'll catch y'all later.